Bada esaldi bat, ia hizkuntza guztietan erabiltzen dena. Hobe irudi bat, 1000 hitz baino. Ona hemen nire irudia. Irudi horiek normalean ez dute behar esaten inolako argibideri, baina hor dut hone behar duela argibideren batero beste. Lehenengo argibidea zea da, hor ikustu duzue Claude Cohen-Tannoudji, irakaslea. Eta ziur naiz agian, esan espanizueke hori, zuetariko gehienok ezen dutela ezagutuko gero beroi ona etorriko denean. Claude Cohen-Tannoudji gaur egun 80 urte ditu. Eta jaio Argelian jaio zen, Argelia Frantzia zenean. Han eman zituen lehenengo 20 urteak Argelian. Baina jakintzazue Cohen-Tannoudjiren ahaideak horiek igez egin zutela Espainiatik, inkiziziori igez hain zuzen, hain justu, eta joan egin zirela Tangerrera. Tangerretik gero Argeliara, eta alegia izena Cohen-Tannoudji hori justu nahi du ezan, Tangerreko Cohendarrak. Cohen-Tannoudji gero, 1953an Parisera joan zen, unibertsitate ikasketak egitera, eta han Ekol Normal Superioren onartu izan zen. Han eman zituen 4 urte ikasten, eta ikasi eta gero soldaduzkain zuen. Lege zarreko soldaduzkain justu. 29 hilabete. Ez da gutxi. Horrengo eskondu egin zen, oraindik bere emaztea den Jacqueline eta hemen gurekin daukaguna. 1960an tesi egiten jardun hasi zen, eta 2 urteren buruan bukatu egin zuen, 1963an. 1962an barkatu, orduan Pariseko Unibertsitateko profesore izendatu egin zuten. Eta 10 urte beranduago, College de Frantzeko profesorea. Azkenengo 40 urtetan han egonda. Baina gatozen berriz irudira. Irudi horretan, ikustu duzue, beste 2 Nobel sari ere badaudela. Cohen-Tannoudji, Alfred Kastler, eta han SH jartzen duena, SH da Serge Haroche. Eta Serge Haroche da iazko, alegia 2012ko Nobel saria ere bai. 3 Nobel sari hauen laborategi berdinekoak dira. Eta hauxe da nik uste dut, irudi on bat, adierazteko Newtonen ezaera, hain urruti ikusi egin dut, nire aurretik izandako erraldoien lepora igo egin naizelako. Jakintzazue, 3 Nobel sari hauen artean badagoela erlazio bat. Eta erlazio hori irakasletza erlazioa da. Alfred Kastelek Cohen-Tannoudjiri zuzendu egin zion tesia. Eta Cohen-Tannoudjik Serge Haroche. Beraz, Cohen-Tannoudjik Alfred Kastelen bizkarretara egozen, eta orduan bera zen Alfred Kastel zen erraldoia. Ondorengo, Serge Haroche izan zen gure gaurko erraldoiaren gainean igozena. Beraz, deitu dezagun, dei dezadan gaurko gure islaria, Claude Cohen-Tannoudji profesorea, zientziako, fizikako erraldoietariko bat.
Thank you very much for your presentation. Thank you very much also for your invitation, Miguel, for your invitation to come here I think for the 4th time in Donostia. I'm so happy to be here again. And thank you also for what you have done, you and your team, for making science popular and enjoyable for a lot of people who are in this room. So what I would like to discuss this afternoon, to discuss of light and matter. You know, understanding light, matter, and their interaction is a very central question in physics. It has been at the origin of a lot of revolution, both conceptual and technological, like the relativity, quantum mechanics, and the laser revolution. Also, when you consider light-atom interaction, you see that when you observe light emitted by atoms, we get information on these atoms. But that's not the only point of view. What I would like to show you in this lecture is that atom-photon interaction can be also used in a different perspective as a way to act on atoms, to manipulate them. So let me first start with reminding the basic interaction processes between atoms and photons. There are emission processes where the atoms go from an upper level to a lower level by emitting a quantum of light, a so-called photon. There is the reverse process where the atom goes from A to B by absorbing a photon. And of course, conservation of energy implies that the difference of energy between the two states is equal to the energy of the photon which is emitted or absorbed. And you see that if you measure nu with the spectrometer, you measure EB minus AA. You measure the difference between two energy levels. So this is why light is an essential source of information on the structure of atoms and also for detecting their presence in various types of media, in particular in astrophysics, for example, in the planetary atmosphere and so on. And since the development of many light sources like lasers, synchrotron radiation, spectroscopy has made a dramatic progress in the last few decades. But what I would like to show you today is that light is also a tool for manipulating atoms, because when an atom absorbs a photon, it acquires some properties of this photon, its energy, its angular momentum, its linear momentum. So by choosing the properties of the light beam which excites the atom, you can change the properties of the atom. And I would like to give you two examples. First, optical pumping, which use polarized light for polarizing atoms, for putting all the magnetic moment parallel to the same direction, that based on the conservation of angular momentum, and also laser cooling, where you use light coming from a given direction to change the velocity of the atom and to cool them. That based on the conservation of linear momentum. So let me first discuss optical pumping, which is the transfer of angular momentum from polarized photons to atoms. Atoms have an angular momentum. They are like spinning tops. They have an angular momentum, g, which, as most physical quantities, quantized. The projection of g along a given axis takes only discrete values. For example, in the simple case of a spin 1/2, the spin projection along a given axis takes either plus or minus, spin up or spin down. Since this rotation involves charge, the atom has also a magnetic moment, which is also quantized. It has two possible values corresponding to the two directions of the spin. So if you put a magnetic field, these two states have different energies, and the difference between the two energy levels of the spin is proportional to the magnetic field. And if you have transition between the two states, which flip the spin from up to down or from down to up, you get what is called magnetic resonance, which is a very important technique for studying physics, chemistry, biology. Now, what was the motivation of optical pumping? If you take an ensemble of atoms at room temperature and in low magnetic field, the two populations of the two spin states, up and down, are nearly equal. You have a very small difference of population. But if magnetic resonance signals are proportional to the difference of the two populations, spin up and spin down. So they are not easy to get, except if you consider a large number of atoms, which explains why magnetic resonance is usually done on solids or liquids. So how can you increase this polarization? And that was the idea of Kastler and Brossel. The idea is that if you take polarized light That's simple to do by a polarizer and quarter wave plate. Then the photon associated with this light beam have an angular momentum. And when the atom absorbs a photon, it gains this angular momentum, it becomes polarized. So by absorbing polarized photons, atoms can gain the angular momentum of the photon and become polarized. And you can get in this way high degrees of polarization, nearly 90%. And you can detect magnetic resonance in gases, in very dilute systems. And that the two people, Alfred Kastler and Jean Brossel, who created at the end of the 1940s, beginning of 1950, a group working on this method, which are called optical method. Okay, so let me now be a little more precise. Suppose that you have atoms in a cell here, and excited by light which is circularly polarized, high circularly polarized. The electric field rotates counterclockwise along the direction of propagation. Now, suppose, let me take a simple example where the two states of the transition, G ground state and E excited state, have both a structure corresponding to two spin states. What we call, they have both a spin 1/2, an angular momentum 1/2. So in the excited state, you have two spin states, minus, plus, minus, plus. In fact, in physics, the angular momentum is measured in units of h bar. H bar is equal to h, the Planck constant, divided by 2 pi. So this angular momentum is minus 1/2, this one is plus 1/2, and the same thing here. Now you can show that sigma plus photon, circularly polarized photon, has an angular momentum equal to plus 1. And the only transition during which the value of the angular momentum increased by plus 1 is between minus 1/2 and plus 1/2. So if you use sigma plus polarized light, you selectively excite this transition. This one or this one corresponds to a variation of angular momentum equal to 0 that cannot be excited by sigma plus light. So you prepare the atom in the upper state plus 1/2. And when the atom falls back to the ground state, if it falls back in this way, it can repeat the cycle. If it falls back in this way, then it is trapped here because there is no sigma plus transition starting from plus 1/2 in the ground state. There is no plus 3/2 state in the excited state. So you see, you have some sort of a pump which empties this level and which fills this one. This is why this is called optical pumping. It's a pump due to light which polarizes the atoms. And you can get, if the relaxation process which equalizes the two populations are weak enough, you can get very high degrees of polarization. And the important point also is that you see clearly on this picture that the amount of absorption is proportional to the population of this state, because only atoms in this state can absorb sigma plus light. So by monitoring the absorption, you can detect any change of the population of minus 1/2. Any change which could be due to collision or to magnetic resonance transition between these two states. This is why this is called optical detection of magnetic resonance. And that's very sensitive because it's much easier to detect an optical photon than a radio frequency photon, which has a much lower energy. So these have had a lot of fundamental and practical application. I will just describe two. First, a practical application. And this practical application, Kastler and Brossel didn't have any idea of it when they invented the scheme. It appeared a long time after. And the idea is that if you take polarized helium, polarized by optical pumping with 90 degrees of polarization, and if you have a patient breathing this helium gas with a mixture of air, then you fill the lung with polarized gas. And the degree of polarization is high enough for detecting magnetic resonance and to make magnetic resonance image of the cavity of the lung. You know, usually MRI, magnetic resonance imaging, use the protons of the hydrogen atoms of the water molecules which are in the blood, in the bone, in the flesh. You don't detect the empty part of the body. This is, for example, a proton MRI of the chest of a patient. But with helium, you see now the cavity of the lung. And you can detect if a patient has an asthma or if it's a heavy smoker and so on. So you have a medical application of optical pumping which was not at all predicted at the beginning. I would like now to describe an application in fundamental physics. There are many others, but I've chosen this one because I will show you that it is also useful in laser cooling experiments and in cavity QED experiments. And this is what is called light shifts. You know, when you calculate, when you do the theory of atom-light interaction, you can show that if the light is slightly detuned from resonance, then the atomic levels are shifted by light, by an amount, delta Eg, for example, for the ground state, which is proportional to the light intensity, and which has the same sign as the detuning between the light frequency omega L and the atomic frequency omega A. For example, if the light is detuned to the blue, omega L is larger than omega R, the shift is positive. If the light is detuned to the red, omega L smaller than omega A, the shift is negative. And you know, if you have two Zeeman sublevels in the ground state, usually they have different light shifts. You know, you have two ways of considering this effect. The first one is it's a perturbation. When you do high-resolution experiments, you don't want to have something which changes the atomic frequency. And the light which is used in optical pumping experiment can change the frequency you want to measure. So it's a perturbation. But what appeared a few years after is that this perturbation can be also considered as a tool for manipulating atoms and photons. And I will describe a few applications of that. Before doing that, let me tell you how this effect was observed for the first time. It was using an effect of the polarization. You know, suppose that I come back to this one-half transition, and you excite with the laser beam, with the light beam, either sigma plus or sigma minus polarization. You see that depending whether the shifting light beam has a sigma plus or sigma minus polarization, you shift this level or this level. And you shift it, you know, in this direction for sigma plus for mg equals minus 1/2, and in this direction, mg equals plus 1/2 with a sigma minus excitation. That's the Zeeman splitting between the two sublevels produced by a static field. And you see that depending the perturbing light as a sigma plus or sigma minus polarization, you increase or you decrease the splitting between the two Zeeman sublevels. So the magnetic resonance, optically detected with a resonant beam, undergoes the light shift, which has not the same sign, depending the shifting beam is sigma plus or sigma minus. And this is the experiment that I did in my PhD work in 1961. And you see that you have atoms, mercury atoms, which are here, which are optically pumped with a resonant beam, and which are perturbed with the second beam, which is off resonance, and which is sigma plus or sigma minus polar. And you see that without the second beam, this is the magnetic resonance curve, and depending on the perturbing beam is sigma plus or sigma minus, you see clearly a shift of the magnetic resonance curve, a shift which is extremely small, only half a hertz, but which can be detected between the ground state. Lifetime is very long, and the magnetic resonance curve is extremely narrow. Okay, so now I switch to the second application, to the second example of manipulation, laser cooling and trapping, which is due to transfer of linear momentum from photons to atoms. Let me first give you a very simple picture, which can be understood very simply without any calculation. Suppose that you have a target, C, here, which is bombarded by a beam of particles, P, coming all from the same direction. So the particle bounce on the target, bounce off, and they exert a pressure on the target which is pushed in the direction of the beam of projectiles. As a result, you know, in more sophisticated terms, you can see that you have a transfer of linear momentum from the projectiles to the target, and this is the force. And you know, this replaces the target by an atom and the projectile by photons. You see that the photon can be absorbed and re-emitted. This is exactly the same situation, and the atom is pushed in the direction of the beam. This is called radiation pressure force. And in fact, this effect has been known for a long time because, as Kepler suggested, it can explain part of the mechanism of the tail of the comet. The comet is an astrophysical object which is surrounded by dust, and the light coming from the sun, the comet is orbiting like that, pushes this dust and gives rise to a tail which is in the direction of the sun, not along the trajectory. With the laser beam resonance, even if the power is low enough, is relatively low, you can show that the force is huge. And let me explain to you in a simple term. You know, when an atom absorbs a photon and goes to the excited state, it does not remain there forever. After a very short time, which is the lifetime of the excited state, the atoms fall back to the ground state. And the lifetime of the excited state typically is on the order of 10 to the minus 8 seconds. 10 nanoseconds. So if you have an atom in a laser beam, it absorbs a photon, it falls back, a second photon, a third one. And since the duration of the cycle is on the order of the radiative lifetime, within a factor 2, the number of cycles per second is 1 over tau is 10 to the 8 second, minus 1, which means that an atom in a resonant laser beam can absorb and re-emit 100 million times a photon per second. Now, each cycle, in each cycle you have a transfer of momentum h nu over c, because Einstein showed that any photon with energy h nu has also a linear momentum h nu over c. So this momentum transfer to an atom of mass m gives rise to a velocity change per cycle, which is h nu over mc. And when you put the number, typically this velocity change per cycle is 1 centimeter per second. So that's a very small velocity compared to the velocity of the molecules in the air around us, which is typically a kilometer per second. But you know, the mean velocity change per second is equal to the mean velocity change per cycle times the number of cycles per second. So it is equal to 10 minus 2 times 10 to the 8 meter per second squared. So it's 10 to the 6 meter per second squared. And since the acceleration due to gravity is 10 meter per second squared, g, the acceleration of an atom, or the deceleration, depending if the two velocities are opposite or parallel, is 10 to the 5g. So this is a huge force. And if you take an atomic beam coming in this direction and the laser beam counterpropagating, with this deceleration, you can stop the beam in 1 meter, which is very fantastic. But there is always an objection that when the atoms start to be decelerating under the effect of the force, because of the Doppler effect, it becomes off resonance from the laser beam, and the force decreases. But there has been a very clever idea of one of my colleagues, Bill Phillips, who got the Nobel Prize the same year as me, which has to use a magnetic field with a gradient along this direction, with a tapered solenoid, it calculated in such a way that the change of the optical frequency due to the Zeeman effect compensates the change of the apparent laser frequency due to the Doppler effect. And you remain in resonance, and then you have a huge deceleration over the whole trajectory. Once the atoms are stopped, they still have velocity around the mean value 0. They have still a dispersion of velocity around the mean value. And in physics, temperature is related to the dispersion of velocity. The greater the spread of velocity, the higher the temperature. So how can you decrease this velocity spread? And the simple scheme is called laser Doppler cooling and use the Doppler effect. Suppose now, instead of laser beam, you took 2 laser beams with the same intensity and the same frequency, nu laser, smaller than UA, the frequency of the atom. If the atom is at rest, there is no Doppler effect. The 2 radiation pressure forces are opposite. They cancel out, and you have no net force. If the atom is moving to the right, like that, the counterpropagating beam has an apparent frequency which is shifted up because of the Doppler effect. So nu L is increased, it becomes closer to nu A, the process is more resonant, more photons are absorbed per unit time, and the force increases. For this beam, the beam is parallel to V, the Doppler effect is negative, and the atoms get farther from resonance and the force decreases. So as a result of the Doppler effect, the two forces are no longer equal and opposite, and the net force is opposite to the velocity. So you have a situation where you have a force opposite to the velocity and proportional to the velocity. This is what is called in physics the viscosity. And this is why people call this scheme optical molasses. It looks like if you have a pot of honey, you know when you have a pot of honey, when you try to move a spoon, the faster you move the spoon, the greater the friction. You have the equivalent of that, optical molasses, but you replace the honey by light. You have a molasses which is produced by light. And this scheme, you can calculate what temperature you could get, the minimum temperature you could get, and you find, with a simple calculation based on the theory of Brownian motion, you find the temperature expected is 100 and 200 microkelvin. Because, you know, in physics, we use the Kelvin units. We start from 0, go to infinity. The room temperature here, if it is 27 degrees Celsius, is 300 Kelvin. So 300 microkelvin is 1,000,000 times cooler. It's already very good. But when people started to do experiments, precisely how they measure the temperature, they switch off the laser beam, so the cloud explodes, and by measuring the expansion, you can measure the velocity spread and you can measure the temperature very precisely, with 5% precision. And the result was very surprising. The result is that temperature was 100 times lower than expected. So that's a very good surprise, because usually it was much worse than predicted by theory. So what was the reason? And in fact, this is where our experience in the lab, done 30 years ago, that was discovered at the end of the 80s, 1988. So that our experience on optical pumping and light shift provided the explanation of this effect. And with a young colleague, Jean Dalibard, we explained this effect in terms of the following effect. You know, when you have two laser beams counterpropagating, they interfere, and you have a standing wave with minimum of intensity, maximum, minimum, maximum, separation lambda over 2, where lambda is the wavelength. Also, the polarization change. If you take the two laser beams with orthogonal polarization, the polarization is sigma plus, and then sigma minus, and sigma plus. So, since the laser is detuned from resonance, you have light shifts. And you have light shifts which depend on the intensity, so which are modulated in space with a period which is lambda, the laser wavelength. And since the polarization is modulated, you have also optical pumping from one sublevel to the other, or from plus to minus, or minus to plus. So you have a situation where the two sublevels in the ground state spin up and spin down. The position is spatially modulated, and the optical pumping is also modulated. You go from this state to this one, from this state to this one, and you have a situation where the poor atom, which is moving to the right, climbs the potential hill, and when it is at the top of the hill, it has a certain probability, high probability, to be optically pumped to the other state, put in the bottom of the valley, and then it has to climb again, put at the bottom of the valley. So you have the situation, exact situation, similar to the situation of the hero of the Greek mythology, Sisyphus, who was condemned to roll up a rock to the top of a mountain, and when he was at the top, the god was putting him at the bottom of the valley and to do the work again and again. That's exhausting, and this is what the poor atom is slowed down, and it is cool. And you can do the theory of this, and you can demonstrate that that explains the result, and that shows that Sisyphus cooling, we call it Sisyphus cooling, can allow you to reach temperature of the microkelvin range, 1 or 2 microkelvin. Also, another application, so that's an application of optical pumping and light shift, which was discovered 30 years before. Another application is trapping. If you take a laser beam like that, and if you focus it, and if the laser beam is detuned to the red, the light shift of the ground state is negative, and it is proportional to the light intensity. It's maximum at the focus of the beam. So the ground state of the atom appears to move in a potential well which it is centered at the focus of the beam. And if the atom is cold enough, it can be trapped in this potential well. This is called a laser trap. And in fact, it works even for biological objects like proteins, viruses, and this is called also sometimes tweezer, optical tweezer. Also, if instead of using a single beam focused, you take standing wave in 1D or 2D and 3D, you achieve a specially periodic array of potential wells in which atoms can be trapped. You have the same situation as a box for X, where the X are trapped in the hole of the box. So it's some sort of a box for X where the X are replaced by atoms. Okay, that's a funny, amusing effect, but it's more important than that because, you know, the motion of an atom in a periodic array of potential wells shares many features with the motion of an electron in the periodic potential well produced by ions. So as Ignacio explained in the first lecture 2 days ago, you have here a quantum simulator. With this scheme, you can simulate effects which are usually observed in solid-state physics, and you think you can vary all the parameters very easily. You can switch off the lattice. You can, if you change one frequency compared to the other, you have a moving lattice. So you can make a lot of new things, and you can get a better understanding of many effects observed in condensed matter. Now, what can you do with these ultra-cold atoms? What kind of application? Mainly 2 great categories. When the velocity is small, the observation time is longer. You can have much more time to observe an atom moving with 1 centimeter per second than an atom moving with 1 kilometer per second. And in physics, the width of the resonance lines you can measure on atoms is inversely proportional to the observation time. So you can measure this transition frequency with much higher precision. You can make what is called high-resolution spectroscopy. And you can make frequency standards based on atomic transition, which are much more precise, more precise atomic clocks. A second application comes from the fact that in physics, any matter particle has also a matter wave, has also a wave aspect, as shown, as introduced by De Broglie. Louis De Broglie, which postulated that with any particle of mass m, there is a wave with a wavelength, lambda De Broglie, equals to h, the Planck constant, divided by m, the product of mass, by the velocity. If the velocity is small, the De Broglie wavelength is large. Atoms moving at 1 kilometer per second have the De Broglie wavelength smaller than 1 nanometer. Atoms with velocity of 1 millimeter per second have De Broglie wavelength of 100 micron. So the De Broglie wavelength becomes macroscopic, and you can observe new effects which are predicted by Einstein a long time ago, which are called Bose-Einstein condensation, where you have a macroscopic number of atoms all in the same matter wave. I will not discuss that because that was a subject that Pedro invited me in 2005 at the celebration of the famous year, 100th anniversary of the 3 papers of Einstein, and I gave a paper, Bose-Einstein condensation, a new form of matter. So I will just give a short description of the first topic. So usually atomic clocks use atomic beams. And since the cesium is defined since the second is defined from a transition of the cesium atom, what people do is they take a cesium beam, moving with a velocity of 100 meters per second, and passing to 2 cavities resonant for the microwave transition of the cesium atom. They move with a velocity of 100 meters per second. Reasonable clock, you cannot go over half a meter or 1 meter. And you can show, that was demonstrated by Norman Ramsey, when you have 2 interaction, two coherent interactions separated in time, but the time it takes from going from there to there, you have Ramsey fringes with the width which is determined by the time of flight of the atom from one cavity to the other. If you have half a meter, velocity of 100 meters per second, the time of flight between here and here is 5 milliseconds. You can go much larger than that. Of course, you could get 2 meters, but it's not practical to have a clock with 2 meter high length. But with cold atoms, you can do something else. You can start with the ball of cold atoms, a cloud of cold atoms, and with laser pulse, you push the atom upwards. And you have a resonant cavity here, and the atom crosses the cavity once on the way up and once on the way down. And an elementary high school calculation shows you that if the height of the fountain is h, the gravity acceleration is g, the time between the first interaction and the second one is given by this equation. And when you put the number 30 centimeters, g equals 10 meters per second squared, you find 0.5 seconds. So you gain 100 factor between the two. And this is called atomic fountain, thank you. Because you know, it looks like a fountain, except that the drop of water is replaced by atoms or molecules. And with this, let me come back a little, just a few typical temperature in the scale, temperature scale here. You know, the interior of the sun is several million of degree Kelvin. The surface of the sun is 3,000 Kelvin. The Earth is, as I mentioned to you, 300 Kelvin, 427 Celsius. The cosmic microwave background radiation, which fills the universe and which is a remnant of the Big Bang, has been measured very precisely to be 2.7, etc. Kelvin. The cryogenic technique using liquid helium or into Kelvin, a few millikelvin. Now with laser cruising, you get 1 microkelvin, and with the condensate, you reach the nanokelvin. So you see, you have a huge 10 or 9 order of magnitude between the liquid helium and the ultra-cold atom, and the same jump that between the liquid helium and the interior of the sun. So let me give you an example of fountain that the Ramsey fringes obtained in Paris by two of my colleagues, Christophe Salomon and André Cléron, with a very good signal-to-noise ratio. And the width of the resonance allows an accuracy of 3×10⁻16. And this represents a clock which, if it was functioning for 300 million years, it will be off by less than 1 second. So you see that's a lot of application. For example, the GPS system depends on atomic clocks. And also now with atomic clocks using not microwave transition, but optical transition, it's possible to reach an accuracy of 10⁻17. And these numbers are so impressive that it is now considered the possibility to put the clock in microgravity. First, a series of experiments have been done in a parabolic flight, where we have a jet doing a series of parabola, and during this parabola, you can make an atomic clock. You see here the people in the plane, in free floating, and a factor 10 has been gained by this technique. And now it has been decided to put the clock in the space station, forming what is called SES projects, Atomic Clock Ensemble in Space. And with this, it would be extremely important because this clock in space will synchronize all clock in the Earth, and in particular all clock of the GPS system. And that would be important for the global positioning system. Of course, also very exciting possibility is that the clock which is in the space station 400 kilometers above the Earth and the clock with another clock in the Earth, you have the possibility to test general relativity, because general relativity predicts that the frequency of the clock depends on the gravitational field in which the clock is put. And the difference delta nu over nu is equal to 10⁻16 for a difference of altitude of 1 meter. Since you have 10 minus 16, you could detect the redshift for 1 meter. Actually, with 10 minus 17, the people who do the clock, optical clock, are obliged to measure the position of the two clocks within a few centimeters, because 30 centimeters correspond to 10 minus 17. But if the clock in space and the clock in Earth, the relative shift is 10 minus 11, it would be possible to test general relativity with an accuracy 100 times better than all previous tests. And in physics, it's always important to test the fundamental theory, because there is no fundamental theory. A theory can be questioned, and that's the main principle of science. You have to test everything. Also, another application is that since the frequency of the clock depends on the gravitational field, you could, by putting several clocks, determine what is called the geoid, the surface around the Earth where the gravitational potential has the same value. Also, a very exciting experiment also is to take two clocks with different atoms, rubidium and cesium, or hydrogen and rubidium, to measure the ratio of the two frequencies during 1 year, and to see if, by chance, the fundamental constants of physics are changing in time. Because there are some cosmological models which predict such a variation. Okay, now just 2 minutes more. Another more recent application of light shift was to consider atoms in a high Q cavity. A cavity with such a high Q factor that you can store a photon for nearly 1 second. And if you have an atom crossing this cavity, like that, with two states, the two states undergo light shift when they are in the cavity, which are different from the two states. And since the light shift is proportional to the intensity, to the number of photons, the two light shifts here are not the same depending on the cavity is empty or contains 1 photon or 2 photons or 3 photons. If you make a pi/2 pulse, you produce a linear superposition of the two states, the dipole moment. The dipole moment acquires a phase shift when it crosses the cavity, which is not the same depending if there is 1 photon or 0 photon. And since the cavity is detuned from resonance, you have no absorption of the photon. The atom crossing the cavity does not absorb the photon. It does undergo the light shift. And you know, that's very interesting, because when the atom leaves the cavity, by making a second pulse, you can determine if the cavity contains 0 photon or 1 photon without absorbing the photon. So you have what is called a non-destructive detection of a photon. Usually, photons are detected by destroying them. When you have a photodetector, you destroy the photon. Here, you detect it due to the light shift without destroying the photon. And this is why Serge Haroche and David Wineland got the Nobel Prize last year for manipulation, quantum manipulation of single quantum systems. Then it's possible to make experiments on a single photon and to detect it without destroying it. That's a very big event. So I would like to conclude with another picture, in addition to the one that you showed just before, a different picture taken just after the Nobel Prize of Alfred Kessler in 1966. That was in October also, in the front of the lab. And you see here Alfred Kessler, Jean Brossel, the two founders of the laboratory. I'm here, so 47 years ago. I had just finished my PhD work 3 years before, in 1962, and I was starting to have my own research group, and my first PhD student was Serge Haroche, who is here. So you see that's a beautiful example of showing how research, basic research, is a long-term enterprise. It's very important to have a group with charismatic person, able to excite people and to have them working in depth on a given problem. That's also a good example of transmission of knowledge. I have been introduced to physics by these two outstanding physicists, and I've been trying to transmit this knowledge to younger people. Thank you very much for your attention.